Hi everybody, I'm finally back after quite a gap on this series. I was busy with other things, not just my professional life. At this point in my life, I have the discipline to allocate strictly hobby time for myself because it's good for my health, I feel happier, and it improves my productivity, my actual day job quite a bit. So that was not the reason. The reason was that my hobby time was taken up by the release of Argon Light, another 8-bit microcomputer, very small, quite high performance, that I and my partners in crime have released a little while ago. So all my free time was spent on that. But now I'm back. I'll add a link in the description to Argon Light in case you're curious about that other project, if you don't know about it already. Today I want to talk about the instruction set architecture. We will talk for the first time about the actual instructions of Talos ES. It will be a more or less theoretical video. It will not be very short. We need to cover a lot of ground, but it will be worthwhile. And I want to start it with a review of the 3 circuits we've built so far, the 3 boards. The last one we've built was the one I'm showing here right now. That's the addressing logic card of Talos. Before that, we did the register file card and the ALU card. These 3 cards were the easiest part of Talos ES. But because it's been a while, I just wanted to very quickly go over the main aspects and the key control signals of these boards, because I'm going to refer to all this when I explain my current idea for the instruction set of Talos. So let's start with the last circuit we covered, which was this, the addressing logic card. There are 4 key registers here. The address register 1, which is composed of these 4 counter chips. Not only is it a register of 16 bits, it counts as well. Address register 2, which is the same thing. It's an address register of 16 bits with a counter. That's the program counter, which is also a counter. And that's the jump address, which is divided in 2 8-bit registers, jump address high and jump address low. And these are the internal bus high and the internal bus low. Now, to control this whole thing here, we need a number of control signals. And that's the important thing that I want to remind you of, because that's what we are going to talk about today. For instance, for the address register 1, we need a control bit called address register 1 count enable. When that bit is active, this register will count one by one upwards. When this bit is disabled or inactive, then it will not count. It will maintain the same value in here. There is also here, if you follow through the inverter, address register 1 load enable. Maybe I'll make it bigger so you can read it better. I'm referring to this right now, the address register 1 load enable, which gets inverted. But when it's active, it allows the address register 1 to latch a value in the internal bus, both the internal bus high and internal bus low, because this is a 16-bit register. We have the same thing for the other one. We have an address register 2 count enable in here, and if you follow this line through the inverter, we have an address register 2 load enable. They serve the exact same purpose. Now there are these 2 transceivers here. These 2 are for address register 2, and these 2 transceivers here are for address register 1. 2 transceivers because it's 16 bits, so we need 2 8-bit transceivers. And when they are enabled, they put the contents of one of these registers on the external address bus, which goes out of the CPU into the rest of the system, into memory and so forth. Now, for them to do that, they have to be enabled through this output enable control bit here and here. So here we have, if you follow this through the inverter, we have the address register 1 output enable, and the same thing on the other side, we have the address register 2 output enabled. When these are active, only one of them can be active at a time, of course. The one that is active will enable these transceivers and will put the contents of the respective address register into the external address bus. It will drive the external address bus with the contents of the respective register. Now, for the program counter, we don't have, let me see, the count enable is pulled up, as you see here. And that's because, well, is that the correct one? Yeah, that's the count enable. The program counter should always count, otherwise it don't execute the next instruction. That's why I just pulled this one up. But the other signals are similar. We have a program counter load enable. So when this one is active, the program counter will latch the value of the jump address register. You regard these two registers as one 16-bit register, the jump address register. When the load enable of the program counter is active, the program counter will acquire the value within the jump address register. We talked about it last time. We also have the program counter output enable, which enable these two transceivers that will put the value in the program counter in the program counter line that goes to the instruction memory outside the CPU. And here we have the jump address high load enable, which is for this register, and the jump address low load enable, which is for this register. If one of them is active, then the register will latch the content of the respective half of the internal bus. So the internal bus high in the case of the jump address high, and the internal bus low in the case of the jump address low. So these are the control bits, and the instructions of Talos will be constructed by determining the value of all these control bits that I've talked about. And not only these on this board, but in all boards. That's what an instruction is. It will, each instruction will correspond to a certain value for all the control lines. So these are the control lines for the addressing logic card that we discussed last time. We also have the register file card, and it has a bunch of control bits as well. We've also discussed this. Let me magnify this a little bit so you see better. These are all control lines. That's the B high load enable for this register here, B high. Then we have the A high load enable, which is the same thing for this register, and so on and so forth. Here are for the buses. This is the external bus input enable for the high part of the bus. We have the equivalent here, the external data bus input enable low, which is for the low part of the bus. I'm not going to go over all the signals, but just for you to have an idea, most of these signals are about load enable or output enable or count enable in the case of the addressing logic. Usually when you want to do a transfer of the value from one register to another, you activate the output enable of the source register and the load enable of the destination register, and you clock them, and then the value will be copied from the source into the destination register. So these are the three main classes of control, or there are four main classes of control bits. Load enables, which enable the respective register to latch a value. Output enable, which takes the contents of the respective register to drive a bus or to drive an internal line. Then we have the count enables, which enable a register to count up. And then you have the control bits for the ALU, which determine whether you're doing an addition, a subtraction. And that's what we can look at right now. That's the ALU. So let me zoom in. No, Siri, I don't want any business with you. So for instance, this is the result register output enable. And if you follow it, it will come from here. It comes from here all the way down, and it will enable this transceiver, which will drive the internal bus low with the contents of the result low register of the ALU. So this is also an output enabled type of signal. This is the same thing for the result high register, an output enabled type of thing. But then you have set negative high and set negative low. Set negative high is here. And these are the fourth class of control bits. They determine which operations will be performed by the ALU. If you remember, the ALU has two halves. That's the high part of the ALU, that's the low part of the ALU. Each half can add or subtract, and if you activate set negative high, then the high part of the ALU will subtract, otherwise it will add. And if you activate set negative low, then the low part of the ALU will subtract, otherwise it will add. And then you have one more control bit here, which is the set full width. With set full width, if it is active, then this ALU, instead of being two ALUs of 8 bits, it will be one ALU of 16 bits. So the registers A high and A low will be treated as one 16-bit register A, and the same for B high and B low. Instead of being treated as two different registers, they will be treated as one 16-bit register B. That's what you get by controlling this line here, set full width. So that's basically it. Everything else you already know. The ALU produces 6 flags, depending on the results of the operation. They are sign flag low, and whether the result in the low byte of the ALU has a sign or not. If it has a sign, it's a negative number. And then the same thing, carry flag low, whether there is an overflow, and zero flag low, whether the result is 0 or not. And then the same thing for the high part of the ALU. So this is, in a nutshell, everything we've looked at so far. So all these little control lines now, how we set them basically means how we design our instruction set architecture, because each instruction will contain the values of all these control lines across the 3 circuits we just looked at: the addressing logic, the register file, and the ALU. Now, how do we go about it? Best way to go about it is using an Excel spreadsheet. I will put this file that you're looking at right now in the repository on GitHub. Links are all in the description. I will try to also put a CVS version of this file in case you don't have Microsoft Excel. The CVS can be viewed using a freely available viewer, so you don't need to buy it, but it will lose the formatting and it will be very difficult to use. So it's best if you do have a license of Microsoft Excel. Just take a drink because I'm doing this in one shot to save time. So let me go over the main columns here so you can orient yourself. On the first column, B, we have the opcode. Each instruction needs an identifier, an 8-bit identifier. In other words, a number. To each instruction corresponds a number. And that number is the opcode. And it starts from 0 and goes sequentially. This is not the smartest way to define the opcode of instructions. The smartest way is choosing the opcode based on how much you can minimize the logic involved in decoding that opcode. Even over 20 years ago, I came up with a method to do this logic minimization. We published papers on this. I'll link to the paper below in case you're curious about how you optimize logic by changing the encoding of a multiplexer, of the control inputs of a multiplexer, which is basically what this is. But I'm not going to use my own invention here because it's a lot of work to do it, and it may make things unclear. I may lose people if they don't know why I'm swapping instructions around and changing their opcodes. So keep it vanilla. And in this case, it's okay because our decoding logic will be memories. It's not the optimal way to do this. If one day I make an FPGA implementation of the Talos CPU, I have this idea of one day putting it in a small little board the size of a PLCC84 chip to use it in other projects as my CPU. If I do that, then I have to do optimized decoding logic and not use memories. Memories are very cheap if you can buy memory chips, but memory inside an FPGA is not a cheap resource. You have to buy very expensive FPGAs to have a lot of memory, and even those don't have really a lot of memory. So at that point I may do something a little more complex, which I don't know whether I will cover in a video or not. I may, but for now I'm not doing any further thinking in how I assign an opcode to an instruction. I'm just doing it sequentially in an order that follows human logic and doesn't take into account minimization at all. So this is the opcode column, and then here we have the assembly mnemonic. Each line is an instruction. Each instruction will have an opcode and an assembly mnemonic. A mnemonic is just a way to write down the instruction in a way that's easy to remember, as opposed to having to write down a number, and in which case you would need a table. So you leave to the assembler to translate the mnemonic into an opcode. I decided that since I'm designing my own CPU, I don't have to follow this old-fashioned way of giving mnemonics to instructions by giving it a set of letters, like 3 letters. Now, this made sense back in the day when memory was extremely expensive, so you had to save as much as possible, so your mnemonics would have to be very short. Here, I figured I'm just going to use C syntax, which everybody knows. So instead of saying load A high, load immediate A high, I'm just saying A high equals a value, and that value is the immediate, an immediate of 8 bits given in hexadecimal. That's why the $sign, that's the hexadecimal for the immediate. So A high equals immediate, A low equals immediate. It's obvious what this does if I write it down this way, and that's how I would define the assembly. You can do the same for all the other 4 registers. You have A, B, and the jump address register. Notice that normally in a RISC processor, the opcode is separate from the numbers identifying the operands. For instance, in the old MIPS RISC architecture, which I studied back at university in the early 90s, you would have a 32-bit instruction word, and then you would get like 6 or 8 bits for the instruction opcode, and then you get 4 bits, if I remember, or 3 bits for each of the operands, each of the 3 operands. Well, you can do that when you have a 32-bit architecture. Talos is an 8-bit architecture, so the entire instruction has to fit into 8 bits. So I'm not separating out the operands from the opcode. Instead, the opcode, this one number here on this column, will identify both the operation and the operands. Not in a way that you can separate. You can't take some bits and say these bits are the operands. No. You have to take it holistically. Number 4, opcode 4, means that register BL will acquire the value of the following immediate. So the whole thing is encoded in one number, and that's because it's an 8-bit architecture that is RISC. RISC architectures, the first RISC machines were already 32 bits. Nobody did 8-bit RISC until the microcontroller age at the turn of the century or late in the 90s. So I am doing it, so I have to go back to basics and do this extreme encoding of everything in the opcode, because I only have 255 opcodes. 256. I only have 8 bits. This is another class of instructions here. Here, A high is receiving the value of the memory address indicated by the contents of address register 1. So address register 1 here is a pointer, points to a location in memory. That's why the parentheses are basically saying that A high doesn't receive the contents of AR1. A high instead receives the contents of the memory location pointed to by AR1. That's what this means. It's a load from memory, essentially. And all these are loads from memory as well. Now, here in the meaning column, I discuss very briefly what the instruction means. And then here we have the actual instruction word. In this line here, we have all the control bits that I've shown you. I just showed you across the 3 circuits we've reviewed. There are several, why is this not, yeah, now it's scrolling. Several control bits, and this is what I'm showing here. I'm showing all these control bits. It's not scrolling, now it's scrolling again. And then at the very end in this column, I have a checksum. It's basically for my own benefit, because I know how many bits should be activated given a certain instruction. And by looking at the checksum, I have a first first line of debugging. If this number doesn't match, it's because I forgot something or added something I should not have added. So these are basically all the control lines we've seen. A high load enable, A high output enable, A low load enable. Let's take another one. Address register 2 load enable, address register 2 output enable. Now it's all there. There are a few lines that are new you haven't seen before. They are these two. That's the immediate high output enable and the immediate low output enable. The immediate register will be in the control card that I haven't covered yet. I'll cover in one of the next episodes. Maybe not in the next episode. I'll talk about the control card, and you will know what these two values mean. There are a few more that you haven't seen. I mean, all this stuff here you've seen: program counter output enable, program counter load enable, result high output enable, result low output enable, set full width, that's for the ALU, set negative high, set negative low, also for the ALU. And then these four you haven't seen yet. This is read and write. These are control lines that go to the rest of the system, and they do exactly what they say they do. This is the read strobe. You send it to an external memory. Once the address is on the address bus, you tell the external memory, okay, now give me the contents of that address. That's the read strobe. That's the write strobe. Just like the 6502, well, the read and write, just like the 6502 and the Z80 have. These two are control lines. They basically mean clear incoming mail flag and set outgoing mail flag. They will also be in the control board. I'm not going to discuss these two right now. I'm just letting you know that they exist. And together, this whole thing here will have 32 control lines, which is 4 times 8 bits. And that's, of course, not by chance. I will use 4 memories to decode the instruction word from the opcode. And that's the key task of the control board that we will see in the next episode. Given an opcode fetched from memory, how do we expand that opcode into the corresponding instruction word? In other words, into the control bits that we need to steer the functionality of the 3 cards, even the 4 cards, because the control card itself has control bits, like I just showed you here, and read and write. And there was something else. I just showed you something else that you hadn't seen before. So that's the spirit of this document, which again will be on GitHub, so you can study it yourself in your own time, calmly. If you didn't understand something I'm talking about, you can always go back to the document and it should be clear there. This is another class of instructions. If you remember, in the last card we looked at, the addressing logic card, the address registers, they could also count. And you could do that count in parallel with another operation. So this is what you see here in the opcodes 19 to 30. We have, for instance, in this 19 case here, we have A high receiving the contents of memory pointed to by address register 1. But then the plus plus says that after we've loaded the contents of memory address pointed to by AR1 into register A high, we will increment AR1. So that's what it means. So that's basically a load from memory plus an increment of the address register. And then here we have the stores. So the memory word pointed to by the address in the address register 1 will receive the contents of A high. So these are basically store operations, and then you have store with increment, just like the other cases. Before I continue showing you the classes of instructions, let me just give you some examples of the control lines so you get an intuition for it. I made the Excel spreadsheet in such a way that you can roll the instruction words to the left and still see what's going on here, what instruction it corresponds to. So let's have a look at a couple of them just to get some intuition. Here, A high should receive the immediate. So we set A high load enable. load enable prepares a high to receive a certain content. And then we go here. The immediate register high output enable is set to 1. So the immediate register will drive a certain line, and the A high will be load enabled and to receive the contents driven into that line. That's how this works. And it's only 2 bits because it's a register to register transfer. And then of course you need the program counter output enable, which is almost always on because you always need to count to the next instruction. And so you have a checksum of 3. And all these instructions here are the same, except that the destination register changes, but they are equivalent. So you have 3 bits for all of them. In the case of a load from memory, it's a little bit more involved. We have, for instance, A high receives the contents of memory in address indicated by AR1. So A high load enable is 1 because A high is the receiving operand. Then we need AR1 output enable because we want to address the memory with the register in AR1, so we need to drive the external address bus with the contents of AR1, so we need to set AR1 output enable. Then we need the external data bus input enable signal, because once you address the memory will reply with the contents of that address. And it's the contents of that address that you want to load into register A high. That's why you have this little parenthesis here. It's the contents of the address. So we have to set the external data bus input enable, so the data that will be put on the external data bus by the memory will be enabled for input into register A high. That's what this means. And of course, we also need to set the internal bus high I/O enable, because the content of the external data bus will go through the internal bus. Maybe I should show it to you. It's in the register file card. Yeah, actually, I'm using the testbed version now, not the simulation version, because this is the one that actually has the correct control values. They are summarized here on the top. So why do we need 2 values? This is the external data bus. That's what goes to memory and comes back from memory. And it has 2 transceivers, because it's there are 2 internal buses, the internal bus high, which is here in this vertical line here, and the internal bus low, which is this, and either of them can drive or be driven by the external data bus. That's why we have 2 transceivers, because there are 2 internal data buses, or 2 internal buses of 8 bits. And the 2 signals that we need, let me make this a little bigger so you see. We need one to enable the transceivers. That's this output enable that you see here and here. And we need one to determine the direction of the transceiver. If you're doing a read, then the direction is from A to B, this way, from the bottom up. And if you're doing a store, then it's from B to A, from the top down. And the direction is given by this little bit here, DIR, direction. So you basically need 2 control signals. One is the external data bus input enable. When this one is active, then the direction is from A to B, from the bottom up. When this is inactive, the direction is top down. It's from the internal bus to the external bus. That's when you're doing a write or a store. But you need to enable these 2 transceivers in order to do an external operation. And that control line, you see this one here, it goes all the way up to an inverter, and it's this line here, that's the internal bus high I/O enable. So when this one is active, then the high part of the internal bus will be enabled to drive the external data bus through this transceiver. And the low part is the same thing. It's driven by this line here, that if you go up and you follow it out, it's the internal bus low I/O enable. So when you are doing a read or a write, you need to activate the I/O enable, be it high or low, one of the 2, and you need to set the direction with the EDBI EDBIE line, which determines whether it's a read or a write. So the first one determines that you are doing an external access to the data bus, and the second one determines whether it's a read or a write. That's why you need two values here, the EDBI and the IBHIOE. In this case, it is the high part of the bus that is enabled to drive the external data bus, because A high is on the high part of the bus. But if I'm doing the same thing with A low, then it's the low part of the bus that is enabled for I/O. That's essentially it. And the EDBI is active in all cases because it's an external bus operation. What else do we need in the case of this instruction? In the case of this instruction here, let's see what else we need. We need the program counter output enable to fetch the next instruction. And we need a read, which is the read strobe, because you're accessing memory for reading. So you need to tell the memory this is a read. Put the value of the address I'm indicating on the address bus, put that value on the data bus. And we have 6 bits to do that. So let me give you some more examples using other categories of operations. These are register-to-register operations. They are the simplest we have. Some of them are 16 bits, like A equals B. Take the contents of register B and puts them into register A. Trivial. So what do we need to do that? Also trivial. A high load enable and A low load enable, because now you're taking A, which is the combination of A high and A low. So you need to enable both for a load because they are the receiving operand. And the driving operand, in this case B, we need to do the output enables of B high and the output enable of B low. And that's it. And of course, we need the program counter to count as well, so we get a checksum of 5. Let's take something else. So now that's the interesting part. SIMD, SIMD, stands for Single Instruction Multiple Data. When this column here is orange instead of gray, that means we are doing multiple operations in a single instruction. Instruction level parallelism, essentially. It's a parallel machine, Talos, after all. When it's single instruction multiple data, it means that we are doing the same operation multiple times on different sets of data. For instance, A high receives the contents of B high, and at the same time, B low receives the content of A low. So I'm doing 2 register-to-register transfers of 8 bits, one in the high part of the internal bus, one in the low part of the internal bus. And we have to set the corresponding control signals correctly. So in this case, A high and B low are both recipients. So we have to set A high load enable and B low load enable, which is here. They are the recipients. Now the drivers are B high and A low. So we have to set, where is B high? Here. B high output enable. B high has to drive the internal bus high so A high can load its contents. And A low, the A low is the other driving operand. So A low output enable should be 1 as well. And beyond that, we need the program counter to count. So 5 is the total. And the same thing goes for the other operations. Then we have 2 ALU operations of 16 bits. Result receives A plus B, result receives A minus B. Remember, if I go back to the ALU is here. The operands of the ALU are directly wired to the 4 registers, to the 4 general purpose 8-bit registers. It doesn't go through the buses. The buses are free to do other things in parallel with the ALU. There is a reason for this, which I will discuss shortly. But what this means is that we don't need to set the output enable of any register because the registers are hardwired straight to the ALU. If you go back to the register file card, this is the testing version, but it should be enough to give you an idea. Here, these drivers here drive the content of the registers straight to the ALU. A high output, B high output, A low output, and B low output, and they don't go through the internal buses here in the center. They are wired straight to the ALU, and they will come out here. That's where they are connected. So we don't need to set any control signal because the inputs of the ALU are always being driven by whatever the contents are of the 4 general purpose registers. So in the case of this operation, all we need to say is to specify that this is a 16-bit operation. We don't need to do anything else. And how do we specify that? Well, set full width is 1. That's all we need to do. And of course, we need to program count. So we have only 2 bits set. Now for this subtraction, now we need something else. We need to set full width, but we also need to set negatives. We need to set negative for the high operand and set negative for the low operand because it's a 16-bit operation. So you need to set negative for both 8-bit operands to pretend they are only one 16-bit negative number. Now, here you have another SIMD operation, 2 subtractions. So what we need to do for this, well, only set negative high and set negative low. We don't set full width because now it's 2 operations of 8 bits, not 1 operation of 16 bits. And the program counter. And now here we get MIMD. MIMD is multiple instruction, multiple data. That's when not only you are doing multiple operations in parallel on different operands, the operations themselves are different as well. So in this case, you have an addition and a subtraction. So what we need for that, all we need to do is set negative low, because for the high byte it's an addition, and if you don't set negative for the high byte, if you don't do it here, if you don't do it, then it's an addition. 0 means that it will be an addition, and 1 here means that on the low byte it will be a subtraction, and that's exactly what you get here. Or the other way around, you do a subtraction in the high portion and an addition in the low portion, so you set negative high and negative low you don't set, so it will be an addition. Now I'm leaving some things out here, like 2 8-bit additions in parallel. Why am I not showing it here? It will come. I will explain this soon. This is another class of MIMD operations where you do 2 ALU operations, an addition and a subtraction, or a subtraction and an addition. And in parallel with that, because remember the ALU does not use the internal buses to get its operands, the ALU is directly wired into the 4 8-bit general purpose registers. So the buses are unused, so you can actually use the bus to do something else in parallel, like you see here in this column. You do a register operation. In this case, this is a memory load. This is a memory load while incrementing the address register. In other words, all the stuff we've seen above, all of this stuff here, all of this stuff here, all these wonderful operations, not the 16-bit ones, only the 8-bit ones, all this stuff can be done here on this column in parallel with up to 2 ALU operations. Wonderful, isn't it? So here you have 3 operations in one cycle. Remember, in a RISC machine, every operation has to take 1 cycle and not more than 1 cycle. And that's the reason, in fact, why I use address registers always. I don't specify the address in memory I want to store into or read from in the same instruction that specifies the store or the load, like in a CISC machine. Because a CISC machine steps through microcode, so you have time to do the multiple data movements required. In a RISC machine, you can't. You have only 1 cycle. So the loads and their stores are always based on the address already preloaded in the address register, be it address register 1 or address register 2, whatever address is in there, that's the address that will be used by the load or store operation. And that address would have to be preloaded by a previous instruction in a previous cycle, because you only have one cycle to do whatever you need to do. So MIMD parallelism here with 3 operations mean 3 operations in a single cycle. And if you look at the control bits, they're just a combination of the control bits for this register operation on the right, and the control bits for the 2 ALU operations. And then you get a higher count. You get 7, 6, 7 bits, because you're combining multiple operations. And in the assembly, that's exactly how you write it in the assembly. What I specify here is how one should write in the assembly. All right, so a lot of operations here. And then we get to the control part. These 2 control operations here, you will understand in the next episode. I will just spell it out to you. One is clear incoming mail flag. This is basically for DMA, direct memory access, communication with an I/O processor. That's what this is for. When an I/O processor is trying to communicate to the CPU, it does that via memory-mapped I/O, shared memory. And to coordinate the use of the system memory, we need these 2 instructions: clear incoming mail flag and set outgoing mail flag. And they set these 2 bits, control bits here, 1 or 0, depending on the case. And then we have the jumps. These are the jumps. I spell out in words what they mean. I also specify more explicitly exactly what the jumps do. This is an unconditional jump. It would just jump to the address in the jump address register. Remember the jump address register? This is the jump address register. Whatever value has been put in there before in a previous cycle by another instruction, the jump will put the value in the jump address register, which has been preloaded, into the program counter. That's basically what it would do. So what are the control bits? Well, let's have a look. Program counter load enable. Do I need to specify a source? No, I don't need, because the source is always the jump address register. The PC program counter can only load a value from the jump address register, and the jump address register always drives the lines that go into the program counter. All you need to do is to load enable for the program counter. So that's what happens here, a load enable. Now, under what conditions? Well, in the case of the jump, it's unconditional. In the case of the conditional jumps here, it will depend on a flag. Now, the flag is not specified in the control word. The control word is what happens if you do jump. Now, whether you jump or not, that depends on the value of the flag, and the circuits to do that I will explain in the next episode. For now, all the jumps are the same as far as the resulting control word. They all would just set load enable for the program counter to receive the contents already preloaded in the jump address register. Okay, now the gaps. I'm calling these pseudo instructions because they are not separate instructions from what you've seen. In fact, if you look at their opcodes, these are the opcodes that you've seen already before, because these instructions are exactly the same as the ones you've seen before. And the reason is the following. Once again, the ALU is designed in such a way that it's hardwired into the 4 general purpose registers. So you don't need to do any kind of output enable or load enable. Well, the load enables are the load enables of the register file. You don't need separate load enables for the ALU, because the registers are hardwired to the ALU, and the ALU always writes to its own internal result registers, result high and result low. And that's done internally within the ALU without going through the internal buses of the CPU. So as a result, the ALU always performs an operation each and every cycle. Always there is an operation being performed. If you don't set any control bits, that operation will be 2 parallel 8-bit additions, because that's what you get when you don't set full width and when you don't set negative high or negative low. If you don't set anything, like you're executing a no-op, a NOP, what will happen? The ALU will take whatever garbage is on the 4 general purpose registers and compute an addition and put the results in the result register low and the result register high. Always. You may not use it, it may be garbage, but it will always be done. Why am I designing it this way? Because this is what allows us to encode not only the operations I already showed you, which are 186 plus 16 here. Notice that the conditional jumps, I start from 255. There is a reason for this, which I will explain if one day I do an FPGA implementation. Or maybe I'll talk about it in the next episode. But there is a reason for that. I just don't want to go into that. But we have 186 plus 16 operations. And then we have all these other operations specified here in assembly. It's a lot of stuff. Look. It's a lot of stuff. Lot of MIMD operations that you can still write in assembly. Everything you see here, you can write in assembly. So why am I reusing other opcodes? And the reason is these operations are subsets of the operations identified by these numbers. So let's take the first one as an example. The first one here, it's result high equals A high plus B high, and result low equals A low plus B low. That's opcode 0. And what's opcode 0? Let's go to the top. Look, it's a no-op. A no-op just sets the program counter output enable so it can fetch the next instruction. It doesn't do anything else. You see, the checksum is 1. So how can not doing anything be the same as doing 2 parallel additions? Well, the reason is what I just told you. The ALU is built in such a way that if you don't set any control bit, it will just do 2 parallel additions to whatever contents are in the 4 general purpose registers. So if you actually do want to do these 2 parallel additions, you will load the correct operands into the 4 registers, and then you will do a no-op. But in assembly, you will write this. You write this thing, this thing here. And the assembler will know that actually this is the same opcode as a no-op, because a no-op, in fact, is 2 additions. It's not no operation, it's 2 additions. Why am I doing this? Because I only have 256 possible opcodes. It's an 8-bit architecture. And because I'm doing SIMD and MIMD, all kinds of parallelism, the number of permutations and combinations of operations that make sense is much higher than 256. So how can I get away with it? Well, I can get away with it by hard coding certain things, by making sure that the ALU always operates, even if there is no control bit and no opcode dedicated to that particular operation. So the opcodes will now be subsets of what the machine is actually doing. And that's how we can get away with 186 plus 16 plus a whole bunch of operations here that go much, much above 256. It's actually almost 500 different instructions that Talos ES can execute. So in assembly, you write this, which is what makes sense to you, but the hardware will be executing a superset of what you're specifying in assembly. That's the essence of it. Did I forget to say something? I don't think so. So what I want to ask you is the following, and I want your help this time. If you are kind enough to help me out, I would much appreciate it. I wrote this spreadsheet, but the only way to really confirm that this is correct is to run a full system simulation, which I'm not sure I would do before I actually do the hardware, because you need to write all the stubs and drivers, and you need to populate all the decoding memories. It's a lot of work. I don't know when I'll get to that. But if in the meantime, after having watched this video and downloading this file from the repository, link is in the description, if you have the interest and willingness to go through this file and cross-check what I did. You have all the material, you have this, you have this, you have this. This stuff is all in the repository. So you have all the circuit information, you have all you need to cross-check this. And if you find that I made a mistake somewhere, I would appreciate it if you would put on a comment below. I will be reading all the comments, and alert me for the mistakes, some inconsistencies, something I missed. I would appreciate your feedback on that. It's easier if you have Microsoft Excel, because then you can use all these features here like I'm showing now. But there will be a CVS file that you can open anyway. So I would much appreciate your help. And it's a chance for you as well to sort of explain to yourself what I'm doing here, so you understand in depth what I'm trying to do. And if I made a mistake and you understand it, you can help me out and let me know. All right, thanks for watching. I will see you next time. It will not take long because I already have the control card more or less designed conceptually, not in schematics yet, but in the simulator I have it more or less designed. I'll share what I have with you probably a day or two after you see this video, and then maybe you can cross-check that as well, but I will talk about that later. In the meantime, thanks for watching. I'll see you next time.